Our next experiment is to set the external force to be an oscillatory force. So again, we think of this mass, and we're going to push down and then up and then down and then up on it. But the key thing now is that this frequency should look familiar. That frequency is exactly the same as the natural frequency of the spring mass we have here with the mass of 1 and a spring constant of 25 newtons per meter. This spring naturally wants to oscillate at 5, and we're going to put a 5 in here. So let's put the 1 in first that we've seen before. We get the disjointed because the frequencies are different. But what if we had the same frequency in both the complementary solution and the non-homogeneous solution? Remember what happens mathematically with that? And then we'll see what happens. So try to predict what will happen in terms of the graph. Aha! Notice what we get in the solution. Because these terms overlap, this has cos 5t, sine 5t, we would have wanted cos 5t and sine 5t in our non-homogeneous part. We have to multiply it by t, though, to get linearly independent solutions. And if you remember that t is an amplitude, then what we get is an amplitude that's growing linearly. You can actually see a straight line through the peaks here and through the valleys down here. And if you look at the spread, and if we extended the time frame a bit and went out for 40 seconds instead, you would see that this expansion is going on forever. So what does that mean in terms of the spring moving? Well, think of it exactly like a swing with your friend on it. We push, and the swing's coming down, and we push and reinforce the push. And then the swing comes up, and we pull the other way, and then we push down, then we pull, then we push. And it's perfectly synchronized. So every time we do this, we're building up more and more energy. We're not diffusing any of it. There's no friction. And what we get is, mathematically, a linear growth in the amplitude. In practice, what's probably going to happen is something is going to break. There's going to be some natural extent where the spring is going to run into the wall or hit something else, and eventually you're going to hit that point with the solution. Now this phenomenon is called resonance. So note the term resonance here, and it's because things are resonating with each other. You can think of this as when you sing and someone cracks a wine glass with the singing, the external force would be the sound waves, and then the object vibrates naturally at some frequency. If those frequencies match, then you get this constant buildup of amplitude in the vibrations of the object, and eventually bad things happen. Now there is a bit of a caveat here. To get this resonance behavior, we have to have exactly the same frequency in the natural vibrations and the external force. In other words, 5.00000 times t and 5.000 times t in both solutions. Of course, that's never going to happen in practice. So you might ask, well, what happens if we're close to that? What happens if we go to 4.9? Does the graph change substantially, and do the formulas change substantially? Well, maybe a little surprisingly, the formulas are exactly what you'd expect. The complementary solution has still cos 5t, sine 5t, because the left-hand side has not changed. But the right-hand side is just a nice cos and sine. The thing is, these frequencies are really close to each other, but there's no t anymore. And yet it looks like things are growing and growing and growing. So what's happening here? Well, the interesting change is, in the last case, they would grow forever. In this case, you see that the oscillations grow and grow and grow and grow and grow. But what would happen is, because your pushing and pulling is just slightly out of sync, slightly different frequency compared to the natural vibrations, eventually the external force is going to get turned so it's just a little bit out of sync, then more out of sync, until eventually it's actually pushing when the mass is pulling, and you're going to start losing some energy. In fact, we can go on a bit further here, and we would see these kinds of oscillations. What I've done is extended the time frame so we can see more in the graph, but you get this phenomenon called beats, where the mass oscillates a little bit more and 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 more, and then less and less and less and less and less and less, and then more and more and more and more and more. And you actually get the same kind of behavior in sound when you play two sine waves that are very similar in frequency. You actually hear this wow, wow, wow in the beats, and that's the phenomenon we're seeing here in the graphical solution. What you notice is initially things look like they're growing very quickly, linearly, but then because things are not quite in adjustment, not quite in alignment between the 5 and the 4.9, it eventually fades away. Let's actually just boost this up to 4.95 and 4.99. So as we get closer and closer, we get more and more longer and longer terms of growth in the amplitude until we get the exact overlap with 5. Okay. So that's a whole collection of other phenomena. Let's just go back and see what happens if we had like 4.5, so not that well aligned. This is where there's not that great an alignment. Notice the amplitude isn't as big here either. If we go back to 4.9, the amplitude here was quite large, 1.5. So you had a real response from this system. If things are not quite so well lined up, then the amplitude you get in the oscillations isn't as big because you don't get a chance to build up the energy in quite the same way between the spring's natural motion and the external force that's being applied. Now, if you're wondering why we get this particular shape, let's take a look back at the notes. There are some nice identities around trig functions, because basically what we have here is a sine of 5t plus a sine of 4.9t. And there are trig formulas you can rearrange to get this, instead of being as a sum, you get it more as a product. One with sine of 5 minus 4.9t, and then that multiplied by a sine of 5 plus 4.9t. There are more details than that. This is basically the structure of what you'd get though. And if you notice this is going to be approximately 0. It's going to be small anyway. This is fairly high. It's just a reasonable number to have for a frequency. And this, you can think then as a high frequency signal, so something that's oscillating pretty quickly, and this is the amplitude. Well, if I have an amplitude that's defined by a sine function with low frequency, there's our low frequency sine wave, and then we have inside of that, going up to the boundary and back down to the negative boundary and so on, we have the high frequency oscillations happening there. So there's some quite fun math. For now, we're not going to sweat that too much. It's just enough to know that when you get close to that perfect resonance and then gradually move away from it, you don't lose the resonance all at once. It's just a gradual decay into this beats phenomenon, and then gradually it gets less and less structured. And when we get down to 4.2, then we start seeing what look a little less coherent, a little more random. And if we get down to 3, we start seeing just more jagged stuff, again with very low amplitude, relatively speaking. And if we had 2.25, we just see essentially random jiggling of the mass. So it's an interesting exploration of what happens when your frequencies match perfectly and when your frequencies are close to match but not perfectly matched versus wildly different, like these two cases here.